Good morning, friends. Today we have an introduction with partial differential equations. Before partial differential equation, we will see what is differential equations. Differential equation, it contains the derivative of a function and a function, or it is a relation between it relates function and its derivative. So that kind of equations are known as a differential equation. In that differential equations, we are having ordinary differential equations known as OD and partial differential equation known as PD. Basically, OD, it relates a function of a single variable and its function. A function of a single variable. Here, y is a function of single variable x. So y is a dependent variable and x is known as independent variable. So dy by dx, that is a derivative of a y with respect to the x, and function of y, it may be x plus y, xy, or whatever may. So xy is a function of y. So it is a relation between derivative and its function. That kind of equations are known as a OD. Another class PD. PD, it is a PD basically deals with the multivariable functions. The dependent variable z may be dependent of function two or more independent variables. Here, independent variable is x, independent variable is y. So d by z by d by x plus d by z by d by y is equal to the x plus y by z. So it is a partial derivative of z and a relation between a function x, y, z. So that kind of equations are known as partial differential equations. So let z be a function of two or more independent variables. Then an equation involving z, its independent variables and partial derivative of z is called as a partial differential equations. So example is z by d by x plus d by z by d by y is equal to x plus y plus z, or z into d by z by d by x plus d by z by d by y is equal to x. Now, when we are going to see the partial differential equation, we should understand what is the order of PDE. The order of highest order partial derivative occurring in the PDE is known as its order. It may be first order, second order, or third order. Here, let an example. D by z by d by x plus d by z by d by y is equal to x plus y plus z. Here, it is a first order derivative because the partial derivative of z is a first order with respect to the x, as well as partial derivative of z with respect to the y is also first order. So that kind of equation is known as a first order. Then z d by square z by d by x square plus d by z by d by y. Here, the highest order derivative is second order. So this equation is a second order PD. Here, d by z by d by x bracket square plus d by cube by d by cube z by d by y cube is equal to 2x d by z by d by x. The highest order derivative is third of d by z. This is a third order derivative. Why? D by z by d by x bracket square. It is not order of equation. The order of equation is d by cube z by d by y cube. Now let us see where the partial derivative involved in our engineering field. You can find a wide application of partial derivatives differential equations in the engineering field. Wave propagation, fluid flow. Fluid flow may be air around wings, water in pipes, material transport, weather, which consists of large system of coupled PDEs, vibration, mechanics of solids, stress strain in materials, heat flow and distribution, electric field, magnetism, diffusion of chemical. So these are the number of we can see field where the partial differential equations are involved, which requires in these different fields. We requires partial differential equations. We have to solve the partial differential equation to solve these different phenomena in the field of engineering. If we consider a weather prediction, it is again deals with the heat transport and cooling, advection, dispersion, radiation of solar heating, evaporation, air movement, heat transfer at the surface. So to predict the weather, one need only to solve a very large system of coupled partial differential equations for momentum, pressure, moisture, heat, etc. So we can have the partial differential equations containing this number of parameters. So the based upon that we can have the prediction of weather conditions. Now, how the PDEs are occurring in the engineering field? We can have the simple example is wave d by square u by d by t square is equal to c square d by square u by d by x square. 1D heat flow equation is d by u by d by t is equal to c square d by square u by d by x square. Two-dimensional heat flow is d by square u by d by x square plus d by square u by d by y square is equal to 0. Now let us see the classification of partial differential equation. We are have a standard or the generalized form of partial differential equation is a into delta square u by delta x square plus b into delta square u by delta x delta y plus c into delta square u by delta y square plus any function is equal to the 0. Now taking the coefficient of delta square u by delta x square, coefficient of delta square u delta xy, or the coefficient of delta square u into delta y square, we can calculate the certain value b square minus 4ac. Based upon this value, we can have the classification as either elliptical, parabolic, or hyperbolic. B square minus 4ac is less than 0. That kind of equation is known as elliptical. B square minus 4ac is equal to 0. That equation is known as a parabolic equation. And b square minus 4ac, if it is greater than 0, that equation is called as hyperbolic equation. So these are the three class of partial differential equation. Now, after that, basic. Let us have the understand the method for the solution of partial differential equation. Partial differential equations are solved with the help of finite difference method. Finite difference method involves the derivative appearing in the equation. The derivative appearing in the equation and the boundary conditions are replaced by their finite difference approximately. So derivative appearing in the equations are replaced by their finite difference approximately. That is the basic of finite difference method. Then the given equation is changed to a difference equation, which is solved by iterative procedure. The process is a slow but gives a good result for boundary value problems, as well as it is easy to computation. We can convert this problem into the program and we can carry out the calculation with the help of any computer or the calculators, electronic computers. Now, finite difference derivative. Let us understand how finite difference approximation to the derivative. Now, let us see finite difference approximation to derivative. Let us consider a rectangle region R in the xy plane as shown in this figure. This is a rectangle region R shown in the figure of y and x. It is divided into the rectangular networks of side delta x is equal to h and delta y is equal to k. Delta h x is equal to h and delta y is equal to k in the y direction, in the x direction. So region is divided into the mesh or the grid. It may be designated as grid point. So the part of intersection of dividing lines is called as a mesh point, nodal points, or grid points. X comma y, x comma y minus k, x plus h comma y. These are the number of grid points or the nodal points. These xy points may be designated as in terms of I and j for the purpose of simplification. Here P is designated as I comma j, then this point is designated as I plus 1 comma j, this point is designated as I minus 1 comma j. Likewise in the y direction it is j plus 1 or in the j minus 1. Likewise we can design the or we can define the nodal points in terms of xy or in terms of ij. Then by final different approximation for the PD in the x direction, Day by u by day by x is a partial derivative of y with respect to the x. It can be approximately replaced as u at x plus h comma y minus u at xy divided by h. This is u value at x plus h comma y minus u value at x comma y divided by this grid size or the mesh size, that is h, in the direction of x. Thereby u we are taking differentiation in the direction of or with respect to the x. Thereby u by day by x. It can be also written as u at x comma y minus u at x minus h divided by h, or it can be written as u x plus h comma y minus u at x minus h comma y divided by 2h. Likewise, we can have delta square u by delta x square is equal to u x minus h comma y minus twice of u at x comma y plus u at x plus h comma y divided by h square. You can easily understand this formula from your grid structure. U at x plus h comma y, u at x minus h comma y, or u at x comma y. Using this, you can either replace delta u by delta x, or you can replace delta square u by delta x square. If we are replacing x comma y with respect to the I and j, you can have ux, that is delta u by delta x, can be written as u I plus 1 comma j minus u at ij. It is equation number 1. Then ui comma j minus ui minus 1 comma j divided by h. It is equation number 2. Likewise, we are having equation number after 1, 2, 3 used to replace u x or deba u by deba x. We can have relation for deba square u by deba x square. That is u x x. ui minus 1 comma j minus twice of uij plus ui plus 1j divided by h square is equation number 4. Similarly, we can have the partial replacement for the partial derivative in the direction of y or with respect to the y. That is deba u by deba y or uy can be written as ui comma j plus 1 minus uij divided by k. Here ui at I comma j plus 1 minus u at I comma j divided by this grid size, that is, or the step size, that is delta y, that is k in the direction of y. So we can have the relation for deba u by deba equation number 5, 6, 7. We can have the relation for deba square u by deba y square uyy, that is u I comma j minus 1 minus twice of ui j plus ui j plus 1 divided by k square. That is equation number 8. So replacing any partial differential equation by their corresponding approximation using equation number 1 to 8, we get a finite difference analogy. We get a finite difference analogy of the given partial differential equation. Okay, so this is the basic about the finite difference method. Now let us understand what is elliptic equation. Elliptic equations are of two types. First one is of Laplace equation and second one is of a Poisson's equation. Let us understand what is the difference between Laplace and Poisson's. Laplace equation, del square or delta square u is equal to deba square u by deba x square plus deba square u by deba y square is equal to 0. That is Laplace equation. And Poisson's equation, deba square u by deba x square plus deba square u by deba y square is equal to function xy. So here, this is a function xy and this one is a 0. So this is the basic difference between Laplace and Poisson's equation. Now to solve the elliptical equations. Now what is the solution of any elliptical PDE? Now, before that, understand where the elliptical PDEs are can be come across. Elliptical PDEs, Laplace equation arise in case of steady flow and potential problems, while Poisson's equations arise in fluid mechanics, electricity, magnetism, and torsion problems. Now, the solution of these equations is any function u x comma y, which is satisfied at every point of region R subjected to a certain boundary condition specified by a closed curve C. So closed curve C defines the boundary conditions, and by closing this closed curve, it's enclose a certain region R. So we can have to determine the any function u comma x comma y at any point of this region. We have to identify the function u at any point x comma y which satisfies these boundary conditions specified by the curve C. That is a solution of this particular elliptical partial differential equations.